to say how much work does it take to charge a capacitor to a certain charge Q. So that's kind of the idea of the derivation. Derive how much work it takes. Yeah, this is electrical work. Electrical work it takes to charge the capacitor to a certain charge. Certain charge Q, or let's say capital Q. So assume that the capacitor is initially uncharged. So let's say it's an initially uncharged capacitor. So the analogy I use for this is kind of like almost like this. Imagine you have a ball. You're trying to find small, imagine you have a bunch of balls like this. And you're trying to lift them onto progressively higher and higher elevations. So let's say this one, I'm going to give it slightly small elevation. So then how much work does it take to lift this ball and place it here? Okay, so then this is going to be the work required would be mgh, and this is h1, mgh1. So then imagine that this is something like a cylinder that's kind of coming up from the ground and starting to, something is electronically pushing it up. So I'm trying to give you a little visual. So then you put this ball and it takes that much work. And then you go to grab that ball and you're going to put it, but by the time you grab that ball, the cylinder is now higher. And now it's got one ball in there. And now the height is h2. So then how much work does it take to put the second ball there? Then it would be mgh2. And assume all of them have the same mass. You see? So something is kind of electronically lifting it. So now you take that second ball and you put it there, and it took that much work, mgh2. Then you grab the third one, and by the time you put it, the cylinder is up. And now you put the third ball there. Okay, then it takes mgh3, and then so on, right? And then the total work done to put all those objects would be the sum of all these works. You see? And that would be the total work done. And then the total potential energy of the system will be equal to, now this is slightly different because it's not quite the same analogy as this, because the electronic system is doing work to lift this also. So it's not a perfect analogy, but the idea is that the total work done on you lifting these should be equal to the potential energy that they have when they are at the top, right? The net potential energy that those balls have. So that's kind of the analogy that you're going to say here. The small amount of work, dW, that it takes to take a charge from the battery and to go put it on top of the plates is equal to the dW is Q times the potential times the let's see, this is the work, the times the voltage difference of the plates. But remember, voltage difference of the plates is, we don't necessarily always write delta V, so I'll just write V. Right? So initially, there is no voltage difference of the plates if it's an uncharged capacitor, right? There's no charge. So V is 0. So it takes almost no energy to put the very first small little charge on the plate, right? So now the plate has some small charge on there. Let's say those are, each one is 1 picocoulomb of charge. So then you put pico, it spreads. Okay, now you're going to take the next picocoulomb of charge. So what has happened to the potential energy of the two plates? It's rising. But in this case, it's not rising because of an electronic system. It's because the battery placed the charge there already. I guess you could say it's rising the electronic system because it's run by the battery, right? So the battery placed the charge there. By virtue of that, the voltage of the capacitor went up slightly. So it's kind of, that means the voltage went up. So the thing going up in this instance is the voltage of the plates. Or more correctly, I should always be saying the voltage difference between the plates is getting bigger as you're putting more charge. The voltage difference, the delta V, right? But I'm not always going to write delta V. So then I'm saying the delta W, the small increment of work that it takes, so that the next charge that you're putting there, it takes a little bit more work. Next charge, it takes a little bit more work. So this would be the small increment of work. These would be all your little dWs, right? So these are all dW, 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 dW. So this could be dm, 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 and then this would be, then you can make the integral problem, right, over here. So that's kind of the idea, is to make this into an integral problem. So how can I make this into integral? Is here's the next step. I'm going to say the small increment of work that it takes to take an arbitrary charge Q to place it on that capacitor is the Q that I'm taking times the voltage at that instance. So this voltage here was the initial voltage, right? So then I'm going to take the voltage at any random instance, right? Voltage instantaneous, right? So then what's the equation between capacitance and voltage? So we have C is Q over V. In other words, the voltage difference between the plates at any instance is the charge that has accumulated on it over its capacitance. Okay, so you have here dW is equal to, oh, this, I'm going to call this guy dQ. dQ times the voltage is Q over C. Oh yeah, that's the way it goes. In other words, this is the charge that has already accumulated there. So this gives you the voltage of that capacitor. This is an incremental dQ amount of charge that the battery is going to take and place it there. And this is the work that it's required. And now we can integrate that between Q initial and Q final. That's the total work required for the battery to charge that plate. And once it charges it, then you can disconnect it. Then that's the potential energy of the battery, the capacitor, the stored energy. So after you've placed all the balls and the system looks like this, and you've got a bunch of balls. Now, if those fall on you, of course, that's a lot of energy to do damage, right? So that means that's their potential energy, is how much work it took. You're adding up all the work that you took to put it there, right? And then that gives the ball, all those collective balls of potential energy to do harm. So in this case, the charges that you place there, once you disconnect the battery, that capacitor can do some good for you. It can, let's say, charge a flashlight, like we saw yesterday, the flash in a camera, right? So then if you integrate this, what do you get? It's an easy integral. The work is, so then it's just C is constant, right? And then dqq, so then what the integral of that is q squared over 2, right? There you go. So that's the potential energy stored in the capacitor. Half q squared over c. So a lot of people, so they look at this equation, q squared over 2c. It's a little mystery where that comes from. You know, why is it q squared? Where did the 2 come from, right? This is sort of magical. Where did this 2 come from? Why is the c on the bottom? Of course, you can argue in terms of units. In terms of units, it has to have units of Coulomb squared over farads, right? So in terms of units, you could argue it should be q squared over c. But it's harder to argue that there should be a 2 there with units, do you see? Unit analysis has that limitation. So I could argue that units-wise, it needs to be q squared over c because this is Coulomb squared over farads. What's farads? Farads is Coulomb over volt, right? So this is Coulomb squared over farads, Coulomb squared over Coulomb per volt. Coulomb cancels Coulomb. Coulomb volt. Is Coulomb volt a joule? Yeah, Coulomb volt. Is that a joule? Oh yeah, back in the last chapter, we saw that the relationship between potential energy of a charge, right? KQ1, Q2 over R, and voltage is KQ over R. So the only difference between them is that a volt is missing the extra Coulomb. So you can say this is a volt, but if I multiply the volt by a Coulomb, I get a joule. You see? So yeah, Coulomb volt is a joule, you see? So just from unit analysis, you can kind of argue, oh yeah, there should be a q squared over c, but you can't argue the 2, you see? That's the weakness of the unit argument. But now you can kind of see where the 2 came from. It came from the integration and the fact that the amount of work it takes to put that charge depends on the voltage that is already there. And the voltage that's already there depends on the accumulated charge that has built up on the battery, you see? So then that's the Q over the C. So then you have small increment of charge times Q over C, and now you integrate that between the 2 charges. So I'm assuming here that the initial charge was 0, right? Then the work required would be just 1 over C Q final squared over 2, right? And then you would derive this equation. So then how do we derive the other forms of the equation? This one, the QV over 2 and the CV squared over 2. How are those derived? Those are derived by just simply saying C is Q over V, right? Taking the C here and just replacing the C by Q over V. I think those are just more variations of this guy. This is the main one. The first one is the main one. So then you can say the other ones are just, so C is Q over V, right? If you put that here, what do you get? 1/2 Q squared Q over V. And then you're just going to get half QV. So that's the voltage that has built up on the capacitor and the charge, and then that gives you the energy that the capacitor has. So it's just a different way of saying the same thing as like this. And then the other form is to get rid of the Q, and you can say from the top here, you can say Q is CV, and then you put that here, and then you get half CV squared. Cool. Nice. Half CV squared. Okay, so we derived the equation for the potential energy of a capacitor. So now let's put all these things together. We've got the dielectric. We know what the dielectric does to the capacitor. It increases the capacitance. We talked about the variety of different kinds of capacitors, the parallel plates, cylindrical, spherical. And then we also talked about how capacitors add up in series and parallel. So let's put these together and then do some variety of examples.